3,000 Kelvin. The Sun is about 5,700. Sigma Orionis is nearly 32,000 degrees Kelvin on its surface. And astronomers give these colours letters. They call them spectral classes. O for the bluest, B, A, F, G, K, M. And I can explain to you afterwards if you want how this arose. Again, it's a complicated story. But there's a good mnemonic for remembering this, which is O, be a fine girl, kiss me. Which, when it was invented 50, 70 years ago, probably suited the mix of sexes in astronomy. I'm not sure it does now. But there we go. O, be a fine girl, kiss me. From the bluest down to the reddest stars. There's the equation that links the two. What it's saying is that a star with twice the mass of the Sun will have about 1.5 times the surface temperature. Right. Meet the grown-ups. You've got one more rude question to ask them. What age are you? Actually, more importantly, how long are you going to live in this stable state before you start to die? I couldn't think of any other way to present this than just in a table, so apologies to a big table of numbers. And have a good look at it whilst I'm talking. Here are the stars in order of mass, from the lightest Barnard star to the heaviest Sigma Orionis. This is their expected lifespan. That's only an estimate, and you'll probably find slightly different values depending on what text or paper or what you read. But this is a pretty good estimate, I think, of how long they're expected to live. And this is the estimated age that they are now. Can you see how the brightest, biggest star lives the shortest? Sigma Orionis will only live for 10 million years. It was born just 5 million years ago. Whereas Barnard's star will live for, hang on a minute, that's 1,700 billion years. Now, hang on a minute, the age of the universe is about 13.8 billion years. So somewhere between the Sun and 61 Cygni A. That means that we have yet to witness the death of, one of these small stars. We can see the death of all these. They're out there somewhere. But these two, you won't see them for billions and billions more years. And there's the equation that links the lifespan of a star to the lifespan of the Sun and the mass of the Sun and the mass of the star. And there's one last thing to say, and that's about the size of the star. It's a very simple relationship. The diameter of the star is proportional to its mass, more or less. So if you double the mass, you double the size. 18 times the mass, Sigma Orionis is about 18 times the size of the Sun. So, I've told you about adulthood, so I think hopefully I've shown you now that the mass is absolutely fundamental to the adult life of the star. But what about the birth of the star? Well, I told you that stars are born in these dark places, these dark, cold places made up of hydrogen gas and some helium and dust. This is actually a dark nebula called Barnard 139. Remember Barnard? Yeah. He took photos of the sky and he discovered about 300 of these dark nebulas, so they still bear his name. This is the 139th he discovered. And again, this is just a few simple figures. Don't pay too much attention to them, but they're important for the next slide. This tries to give you some idea of the size of these clouds of gas and dust. They're measured in tens of light years, but they're incredibly, incredibly tenuous. You know, they contain 100 or 1,000 molecules of hydrogen in a cubic centimetre. So between my fingers, there's just 100 molecules. The air in this room probably contains, I don't know, about 1,000 billion molecules between my fingers. So these are incredibly tenuous clouds. But they're huge mass. They've got the mass of maybe 1,000, 10,000, 100,000 suns in this cloud. And they're incredibly cold. They're only just above absolute zero, and that's really important. Now this is perhaps the most technical slide. I apologise for this. I couldn't kind of simplify it any further, but a chap called Sir James Jeans, he was a British mathematician. He came up with this equation. Actually, the rigorous version of it is much more complicated than this. This is a simplified version because for me it tells the story. I don't really understand the rigorous version, to be honest with you. But what it's saying is that there's this thing called a gene's mass, mj, which is about 45 times the mass of our Sun times the square root of the cube of the mass's temperature divided by its density. Now, from air in this room, fortunately, this gene's mass, we're nowhere near it. The gene's mass for air at the temperature of this room would be huge. But if you recall, for this cloud here, let's say we take a density of 1,000 and a temperature of 10, and we plug that in here, well, temperature of 10 cubed is 1,000, density is 1,000, so that's 1, the square root of 1 is 1. The gene's mass is 45 times the mass of the Sun. And I told you that these clouds can go up to 100, 1,000 times the mass of the Sun. So basically, this is the yellow point here. These molecular clouds are on the hairy edge, right? They want to collapse. That's what this gene's mass is. It says, if the mass is greater than the gene's mass, the collapse under gravity is spontaneous. This cloud will just plump in on itself. That's the first point. As the cloud collapses, that gravity is converted into heat. Okay? But, and this is the other important point, in the early stages of collapse, when the cloud still is not very dense, but getting denser, the collapse is isothermal. And all that means is that the temperature stays constant. The cloud is able to radiate away the temperature quicker than it's formed by the collapse. The consequence of that, if you think about it with this equation, is that the cloud can fragment, because if the temperature is constant but the density is going up, the gene's mass gets smaller. So this huge massive cloud is collapsing. Now the gene's mass is smaller than the total mass of the cloud, so if it divides in two, each of those individual bits can carry on collapsing. And this is, in a touchy-feely way, the origin of fragmentation and then the formation of stars in clusters. Okay. When the collapsing fragment reaches a few thousand Kelvin, it becomes visible. Remember our graph there that said this is the light emitted, different temperatures? At a few thousand Kelvin, the light moves from the infrared into the visible. And it's called a protostar. And at 10 million Kelvin, provided the mass, the collapse reaches that temperature, nuclear fusion begins. And that means that gravity can now be balanced by the temperature that's produced in this fusing core. And this whole process takes millions of years. So it takes a few million years for stars to form. Now, I don't know if any of you watched I think it was the Stargazing Live, or maybe it was the Sky at Night, but they tried to represent this balance between gravity pulling in and the pressure of heat and radiation pushing out that you have in a star as a tug of war. They said, well, you know, you've got gravity pulling in one way and you've got the pressure pulling in. Look, I wasn't quite happy with that, because gravity does pull inwards and the temperature pushes outwards, but can you see it's a kind of pull-push, not a pull-pull. So I thought the better analogy, well, I'm not saying it's better, it's different. I thought a balloon, really. So this is my blue star. A bit smaller. This is my sunlight star. There you go. You can have that one. And this is my tiny little Barnard star. There you go. And like a balloon, you've got this tension between the rubber wanting to contract, so that's gravity, and the pressure I put in the balloon, which is heat, pushing it outwards. That's what stars are, but they're in equilibrium, they're in balance. As long as this fusion carries on in the middle of the star, they're in balance. That's the best I could come up with. So, when these star-forming regions explode into light, the sight is beautiful. And these are 4 pictures I took of 4 new star-forming clouds. This is the Eagle Nebula, Swan Nebula, the Trifid Nebula, and the Lagoon Nebula. They're all visible in the sun, quite low in the sky. With the eye through the telescope, you won't see quite these colours and brightnesses, but the camera picks them up superbly. So I've got one last question, one last little bit of science. Do stars of different masses form in equal numbers? A very good question. And this chap who was an American, Australian, Austrian, I think. He was born in Austria. So these are his dates. He wrote a paper, a seminal paper in 1955 called The Luminosity Function and Stellar Evolution. And what it says, essentially, roughly, is that the mass of a star that is formed from a fragment in a cluster is roughly inversely proportional to the square of its mass. Sorry, the number of stars formed with that mass is roughly proportional to the square, inversely proportional to the square of the mass. So what that means is, a star, for example, with twice the sun's mass will occur at a quarter of the frequency. Okay? Now to prove that, have you all got those little cards that I left on the chairs? You're a star cluster. You've just come out of a fragmenting cloud. You've formed stars. So what we're going to do is we're going to go down that sequence of stars. We'll get back to it. There it is. And we're going to see how many of you there are. So, how many Barnard stars are there? Everybody's got a Barnard star. Just put their hand up or stand up over there. Yeah. There are loads of you. Loads of you. Yeah. Yeah. Okay? Right, sit down. Thank you. How about 61 Cygnis? How many 61 Cygnis? Yeah, we've got quite a few. Quite a few. How many suns have we got? Yeah, not so many. Not so many. How many Procyons? Yeah, just a few. How many Sirius? What's the special ones? How many Sirius have we got? One or two? That's a special one. That's a very special one. How many Alkades? Just give them 2 hours. How many Sigma Orionis? 1. 1 Sigma Orionis, the biggest star. Okay, I fixed it. But, you know what you can do? You can do your own science from publicly available data. I went onto this database called Visiar, which is a bit daunting at first, but you just got to kind of plug away. And I downloaded the raw data from a paper called The Investigation of the Pleiades Cluster. You know the Pleiades is that beautiful haze of stars. It's the nearest cluster, open cluster of stars to us. You can see it with the naked eye, this little milky patch. It's about 430 light years away. And I analysed the data, and I did this histogram. So these are the range of masses of the stars, multiples of the sun's mass. 1's just under 2, 2's just under 3, and this is their frequency. Okay, there it is. So this is data that was generated back in the 90s that I've just processed to show you the reality of this initial mass function. Right? I want to finish with this diagram. And this is the most beautiful, if you like, expression of all the things that I've said, encapsulated in a single diagram. And this is again the Pleiades cluster. And the thing about clusters is, again, you don't have to worry about distance. So you can just literally measure the magnitude of the star that you see through the telescope. You don't have to worry about how far away it is. So if you want to compare them all, you know they're all at the same distance. You don't have to convert the distance at all. And if you look at all the stars in the Pleiades cluster, they lie in this beautiful straight line. And that's because their mass determines their brightness. The plot, so that's brightness up here, the plot down here is the colour, which is their surface temperature. So if you plot the colour, and redder is this end, and bluer is this end, it's called the colour index against their brightness, you get this beautiful straight line, because mass determines the colour, temperature, and the brightness of the star. Not only that, that's the colour index of Alkade. Remember, that was the second heaviest star. There are no Alkades in Pleiades cluster. That's strange. There are at least 2 of them, I said. Well, the reason is because the Pleiades cluster is 100 million years old. And Alkade doesn't live beyond about 100 million years. So there are no Alkades. In fact, they're here. They're beginning to move off this line. This is called the main sequence. And they're beginning to change, and now beginning to move into Mars area. They've run out of hydrogen in their core. They're having to do something else to keep themselves alive. And just to finally convince you that this beautiful diagram is true, I looked at several of the grown-ups that we were looking at in my talk, and I converted them into the magnitude they would appear at if they were in the Pleiades cluster, if they were 430 light years away. And guess where they fall? There they are. Sirius, it's the brightest. Procyon, the Sun, 61 Cygni. Poor old Barnard's star will be off down here somewhere. It would be too faint for the telescope that did this study to pick up. They're there, huge numbers of them. Huge numbers of them, but you can't see them in the telescopes that we use. So I came up with this final quote. I thought, what summarises the influence of mass on the life of stars? And I thought of this quote from The Lord of the Rings, where the One Ring, which is a bit of an evil thing in Lord of the Rings, but for us it's a beautiful thing, is mass. So one ring to rule them all, and one ring to find them, one ring to bring them all, that's brightness, colour, temperature, and in the darkness, find them. There you go. Thank you for listening.